The average simplex cardinality is a type of dimension for simplicial complexes. The cardinality of a simplex is one larger than the dimension of the simplex. We will see here that measuring the cardinality expectation has nice properties. A finite set of non-empty sets, which is closed under the operation of taking non-empty subsets, is called a simplicial complex. It is a combinatorial finite construction independent of any geometric realization. The f vector of a complex G has coefficients which count the simplices of various dimensions. The first entry counts the number of points, the second the number of edges, the third the number of triangles, etc. It can be encoded into a function called the simplex generating function of the complex. The average simplex cardinality is the mean of the simplex size, but we divide by an augmented number of elements in the complex. The reason is that now this quantity can be expressed as a logarithmic derivative of f at 1. In some sense, the additional 1 in the denominator takes into account the empty set. The join of two complexes defines an arithmetic operation which is a monoid. The zero element is the empty complex. The f function of the sum of two complexes is the product of the f functions of the individual complexes, and this immediately implies that the average simplex cardinality is additive. So again, here's the key idea, is that because of f is multiplicative, the logarithm g is additive, and also the derivative g prime is additive. But this is just f prime over f. As f of 1 is 1 plus the number of elements in G, and f prime of 1 is the sum of the fk's multiplied by k plus 1, number of vertices in cardinality, the additivity is clear. Motivated by the inductive dimension for topological spaces, there is an inductive dimension for graphs or simplicial complexes. It cannot be stated directly in terms of the f vector, but it is recursively defined as 1 plus the average dimension of the unit spheres of the individual points. So we see here an example of a complex. We see the f vector, and we have computed also the average simplex cardinality, which is capital DEM, and then the small dim is the average is the inductive dimension, and the augmented version is 1 plus dim. So for varieties or discrete manifolds, the inductive dimension is not very interesting because it's just for a D variety. It's D. A D variety is just a complex for whichever unit sphere is a D minus 1 variety, and the inductive dimension is then D. Also the maximal dimension is D. But the average simplex cardinality gives more interesting values. We see here on the right, we see a discrete sphere, and we see the computation of the average simplex cardinality there. On the left we see a variety, so it's a bouquet of spheres, and also there we have computed the average simplex cardinality. Recently, Betre and Salinger have shown that the inductive dimension is additive with respect to the join operation. It's a little bit surprising. So now there are three dimensions which have the arithmetic compatibility: the maximal dimension, the inductive dimension, and the average simplex cardinality. For the maximal dimension, for the inductive dimension, we have to take the augmented version. So here we see an example also of a circular graph and a complete graph with two elements. Both have dimension 1, and their sum has inductive dimension 3. That's an example of that identity. I have another example here, the rabbit graph and the house graph. This gives the rabbit house graph when we add them. And we see here both dimensions, the inductive dimension below and the average simplex cardinality above. And you see these are rational numbers and they add up. they are additive. Another example, if you take the sum of two one-dimensional spheres, like in topology, we get a three-dimensional sphere, a three-sphere, and in this case, the inductive dimension is one, augmented version is 2, so 2 plus 2 is 4, which is 1 plus the dimension of the three-sphere. For the average simplex cardinality, that's more interesting. We see here 450 over 301 plus 4/3 is 2554 over 903 for that three-sphere. Now there is a general relation between these two dimensions. So we have the inductive dimension, augmented version, and we have the average simplex cardinality, and so the relation is that the dimension, augmented inductive dimension divided by 2 is smaller or equal than the average simplex cardinality. So we see here also an example, or three examples, in the case of complete complexes, complete graphs, Whitney complexes of complete graphs. There we have equality. That's actually the only case where we have equality. In general, it's strict, and we see a cyclic graph. We see also a sum of two star graphs where the inequality is checked. The proof is not that difficult, so we use that conditional expectation, kind of a conditional expectation inequality first. If we compute the average simplex cardinality of a complex, we can patch the complex up with unit balls, and we have when we take the average of these averages, that's smaller, and then we have an arithmetic result which relates the dimension of the ball with the dimension of the sphere. That just follows from the arithmetic additivity, because the ball is just 1 plus the sphere. It's just a cone extension. And then we can use induction now, and for the sphere is smaller dimensional, and there use the inequality, having proven it there, take the expectations and get the result for in dimension D. Another result is when we look at the barycentric limit, we can take barycentric refinements of graphs, and so if we take the Gn, the nth barycentric refinement, and look at the average simplex cardinality in the limit, we get a rational number which is explicitly given in terms of the Perron-Frobenius eigenvector of the barycentric refinement matrix AD on that dimension. So this is all explicit matrices using Stirling numbers, and the rational numbers can be computed. So here is an example in dimension D equal to 2, where the matrix is a 3 times 3 matrix. So it's an upper triangular matrix, so it has the factorials in the diagonal. And we see here, we started with a house graph. We take the barycentric refinement, and it will level out at a dimension 13 over 6 when n goes to infinity. It's quite interesting to see what happens with that Perron-Frobenius eigenvector when D is getting larger and larger. This goes to a Dirac delta at some point. We don't know where this point is, but here we see a computation in the case of D is equal to 100-dimensional space, where we see the distribution of the simplex cardinalities of a complex. You can start with any complex, it will look like that after 100 barycentric iterations. It doesn't matter how you start, it's just the dimension D is important. And so this function here is actually a vector, 100-dimensional vector, a vector in a 100-dimensional space, and we see here kind of it maybe in 100 dimensions that most simplices have about dimension 75 in that area. So we see here a concentration. There are quite a few open problems. First of all, we don't know whether the average simplex cardinality is bigger or equal when we take a barycentric refinement. This is a linear algebra problem which is not yet solved. We also don't know that exact number, the limiting distribution when d is equal, when d goes to infinity. And furthermore, of course, when we have computed the average, we can also ask about the variance and higher moments, and this is all unexplored. So we have, to summarize, we have 3 dimensions which all have arithmetic compatibility with a join. So there is the maximal dimension, which is trivial, which is the inductive dimension, where it's a recent result, and the average dimension, which is now the new result of us. And there are other dimensions for graphs or simplicial complexes, which we did not look at, which also are not compatible. And in the continuum there is inductive dimension, which has motivated the inductive dimension for discrete, in the discrete Hausdorff dimension, and then there's a Lebesgue covering dimension, which is considered in the continuum. So thanks, this is the end. For more information you can look at the preprint which you see listed here.